Thank you so much. It's such a pleasure to be here in Denmark, the land where I was born. I always learn so much when I come back here, and especially to be here at FundForum International, because I think that your industry is really in the epicenter of that triple revolution that Tom just referred to. We are seeing major transformations in every industry, but especially financial services, due to machine learning, due to the platform revolution, and due to crowd-based innovation. And I'm going to explain a little bit about how each of those is changing the economy, driven at its core by digital technologies. But what's important to understand is it's not simply the technologies that are driving this, it's really the invention of business models and business processes. And those are much subtler and harder to understand, but ultimately much more important. And one way to see that is if we go back briefly to in history, about 100 years ago, when there was another big transformation. That was the transformation from steam power and water wheels to electricity. And although it's not a perfect analogy, I don't think history repeats itself. Sometimes history rhymes, and we can learn a bit from that. So over 100 years ago, most factories, like this one in Lowell, Massachusetts, were powered by big steam engines. And when they introduced electricity, historians have studied this, people like Paul David, and found that they actually did not increase their productivity or performance significantly for over 30 years. 30 years is about how long it takes for a generation of managers to retire or die, and that's how long it took for them to reinvent their organizations to take advantage of this technology. You see, the original tech machines that they used, the steam engines, powered all sorts of equipment all through the factory, but they did it through pulleys and crankshafts. And so the machines couldn't be very far away from the central power source. When they introduced electricity, they simply took out the steam engine and put in the biggest electric motor they could find and hooked up the same pulleys and crankshafts. That really didn't fundamentally change their business or lead to much productivity improvement. Even when they built entirely new factories from the ground up, from scratch, they did the same thing. They put a big electric motor in the middle, pulleys and crankshafts. Often there were vertical factories to minimize the total distance that those crankshafts had to be, but fundamentally there was no transformation of the business. It took about 30 years until you started seeing a new kind of factory, factories that looked more like this, single-story factories with machinery spread out through the factory, and the equipment wasn't based on what needed to be closer to the main power source. Instead, for the first time, each piece of machinery had its own separate motor. Small electric motors, medium electric motors, big electric motors. You see, electricity is much more scalable in terms of its power than the steam engine was. And that meant it was possible to organize work in a new way. Only once they reorganized work and went to this assembly line method with the flow of materials structuring this set of machinery rather than who needed to be close to a power source, only then did you see big improvements in productivity. In fact, we saw a doubling or tripling of productivity in those factories once they rethought their business processes, once they changed the way they did their work. So the lesson is not that technology is unimportant, and it certainly isn't that electricity was a dud. The lesson is that if you want to take care of your business models, you need to rethink how things are organized and not simply plug in the new technology to the same old business models. But now we're in the middle of not just one revolution, but what Andrew McAfee and I call the triple revolution. It's a rebalancing between mind and machine for decision making, between products and platforms for revenue models, and between the core and the crowd for key innovation. And we write about this in our book, Machine, Platform, Crowd. Let me take you through each of those three revolutions in turn and discuss some examples and some lessons for how to organize your business, especially asset management businesses. So the first revolution is the rebalancing between mind and machine. And the lesson here is that while many decisions historically have been made by the hippo, in this case I don't mean a large land animal, historically when important decisions were made, people would gather around the table and the hippo would decide. The hippo is an acronym for the highest paid person's opinion. That's how they made decisions. But now, increasingly, instead of relying on the highest paid person's opinion, we're using facts and data. And the key people who are helping with those decisions aren't hippos, but we could call them geeks. And that's a term of affection at MIT. That's high praise if you're called a geek. Someone who understands data and numbers and can make them sing, someone who can do analysis. And the reason that geeks are on the rise and hippos are on the downswing is not simply because the technology is better for analyzing information, but it's that we have so much more information than we did before. We have, by my estimates, over 100 times more digital data available to us today than we did 10 years ago. So it's a complete sea change in terms of our ability to answer questions based on what we know, not just what we think, based on facts, not just on opinions. And this is driving revolutions. The financial services industry was early in this. Organizations like the Renaissance Fund and the Medallion Fund, Jim Simons, and the other day I had dinner with Tim Brown, not to be confused with Tom Brown, who is the CEO at Renaissance, and they described how their data-driven approach to choosing assets has been incredibly successful, and I think you all know this. Now, he says more and more companies are joining in that, not just in financial services, but you look at industry after industry, and this data-driven decision-making, DDD, is becoming more and more popular because the data is now available. And sports teams that use data-driven decision-making are beating those that don't. Insurance companies that use data-driven decision-making are beating those that don't. And certainly in financial services, that's the case. We even have started using it. We're kind of slow, but we've started using it in academia. I recently wrote a paper using data-driven decision-making to make better decisions about how we hire, promote, and tenure faculty, using it on ourselves. Working with Dimitri Bertsimis and a couple of postdocs, we looked at trying to predict which researchers and which papers would be superstars 5 years into the future. And you can see there's a trend there. A paper that starts off with the lead tends to get a bigger and bigger lead. But we really want to zoom in early on and try to make predictions as early as possible which of the new hires were going to be tenured superstars. And to do this, we used analytics, and we found that we could actually outperform the tenure committees in making these decisions. And what I mean by that is we made a set of predictions, and we were able to predict pretty well who was going to get tenure at a top university like MIT or Harvard or Stanford. But sometimes we got it wrong. But what's especially interesting is when the model got it wrong, if you look at the people that the model said should get tenure but who did not get tenure, and you compare it to the people who did get tenure but the model said should not get tenure, the model's candidates significantly outperformed the tenure committee's candidates in terms of their research output in the subsequent years. So the tenure committees would have been better off if they wanted to maximize overall research impact simply going with our model rather than having the committee make all of those analyses and decisions. But this is a pattern we're seeing in application after application, industry after industry, and it's taking time for it to diffuse through the economy because, not because there's a lack of data or even a lack of models, but because the culture isn't changing. Companies are still stuck with that old hippo-based way of decision making, and it's very hard for them to change and have faith in the numbers and the analytics can do better. So trying to see whether these anecdotes were part of a broader pattern, I worked with Christina McElhern, and what we did was we looked at over 30,000 manufacturing plants in the United States. The United States Census allowed us to survey them all. We got a very high response rate by working with the US Census. We found that if you add 6 words to a survey, it massively increases the response rate. Those 6 words are, your response is required by law. And so we got very good response rate, and we asked about the adoption of these techniques, data-driven decision-making, and we found that over a 5-year period, there was a 3 times increase in the number of plants that we classified as using DDD, or data-driven decision-making. Why were so many plants switching to that method? Well, we found that the plants that were doing it were about 4% more productive and 6% more profitable than their competitors, even controlling for all of the other inputs, management, energy, materials, and other factors. Now that's just the first wave. There's another wave coming on, and that is machines that learn. Not we humans who are necessarily making all the decisions, but increasingly allowing artificial intelligence to help us with those decisions and even make some of the decisions themselves. And the subcategory of AI that's taken off the fastest, that's driving this, is the category known as machine learning, where the machines look at data and come up with decisions on their own rather than we telling the machines how to make those decisions. And the subcategory of machine learning that has been most important is an area called deep learning, using neural networks, especially very large or deep neural networks. So let me give you a few applications of this second wave that have been important. Vision and language, recognizing faces. Those of you who have been on Facebook or elsewhere, you can know that they're recognizing faces. More and more ID systems. When I go to China, I find that I can walk into offices and they'll recognize me and the employees without any ID cards, and voice recognition as well. Interacting with the physical world, and this is the area of robotics. You can see that at the large scale, like automobiles, also at the finer scale, like robotics. And most importantly, problem solving in financial services and many other areas, recognizing patterns. In each of these areas, there's been some important breakthroughs. And let me quantify that a little bit. For instance, there's a very large data set called ImageNet. It has over 14 million images that Dr. Fei-Fei Li at Stanford put together. I've been working with her a bit on some of this. And these images have been classified. For instance, some of them are pictures of apples or oranges and lemons. And historically, machines were not very good at recognizing images. It was one of the things that humans could do, but machines couldn't. But that has changed recently. The blue line shows the progress of machines in recognizing images on ImageNet. And back in 2010, they were pretty bad, 70% accuracy or so. That steep part of the curve is when they first started introducing deep learning techniques, machine learning techniques using neural networks. Geoffrey Hinton and some of his colleagues used these techniques and started winning at ImageNet. And today, all of the teams that are competing in the ImageNet Visual Recognition Challenge use deep neural nets to recognize objects. And as you can see, it got so good to the point where it's about 97, 98% accurate. Last year, they actually ended the competition because it was effectively solved. The teams could almost perfectly predict what the images were. And as a benchmark there, the red line is how well humans do it. I mean, humans are pretty good at recognizing objects, but it turns out that we're not perfect. I have a little trouble telling whether those are oranges or lemons in that diagram, for instance, and sometimes I don't know the difference between an antelope and a gazelle, but the machines are much better now than the humans are at these things. I want to be clear, this doesn't mean that machines are better at all types of image recognition. Driving in a car, they're still working on fine-tuning it and out in the wild, but we're very rapidly reaching the point where these image recognition systems are as good or better than humans in lots of applications. You also probably have some experience with speech recognition, whether you use Siri or Google Now or Amazon Alexa. The machines, I don't think, are quite at human level, but they're getting very close. And today, if you see someone walking down the street and they're talking to their phone, you don't really know. Are they talking to another human, or are they talking to the phone and expecting the machine to answer back? It's not implausible that they're expecting the machine to answer back, and the machine, they're not crazy. The machine often will be able to answer their questions about what movie is playing, where's the nearest restaurant, what's the weather tomorrow. Simple questions like that, not a rich, exciting dialogue or discussion, but we're beginning to get to the point where machines and humans can talk together. I think we're in a really unusual 10 or 15-year period where we went from humans not being able to talk to machines to humans routinely talking to machines. And you got to think about that. That's a very important milestone in history. And there are many other applications as you take these core technologies and allow them to make lots of different kinds of decisions. One of the most exciting ones is in medical diagnosis. Hardly a month goes by when I don't read an article in Science or Nature about how these machine learning techniques can outperform humans at diagnosing cancer or pneumonia in dermatology, radiology, or other areas. And they all work essentially the same way. They look at lots and lots of examples, thousands or hundreds of thousands, or in some cases millions of images of, say, cancer versus not cancer. And then the machine identifies the markers. In some cases, they identify the exact same markers that humans who have gone through years of training would identify. And what's perhaps more interesting, increasingly they are identifying new markers that no human had ever seen before, had ever recognized before, to identify cancer or other diseases. And it's just beginning to have some practical impact. We're not really seeing much economic impact yet. It's very early days. I expect it to grow a lot in the next 10 years. But a paper I recently completed looked at how machine translation was affecting the economics of eBay and international trade. eBay introduced a new machine translation system, and the nice thing from the researchers' perspective was they switched it on for different language pairs at different times. First they did English and Spanish, then they did English and French, English and Russian, English and other languages. And each time they switched it on, you could see, boom, there was a big increase in the exports and imports between those two countries on eBay. The people were able to buy and sell things much more easily because the language barrier had been dramatically reduced. About an 11% increase from just this turning on of this one machine translation system in each pair of languages. So that's a very measurable and concrete example of how machine translation and machine learning more generally is delivering economic benefits. Another big area, as I mentioned, was interacting with the physical world. I won't spend much time on this. You've seen the self-driving cars, robots in factories. This is Baxter, works for about $4 per hour, 24 hours a day, 7 days a week. Not for every task, but certain simple tasks like taking things off an assembly line and putting them into these boxes can do very efficiently. And not all robots look like humans or have arms. Here's one from Kim Lee at MIT. This cheetah robot can run about 28 miles per hour, a little bit faster than a human can run. I saw it one time at the MIT track. It was running laps around the track, and they were throwing chairs and other objects in front of it, and it was leaping over them. So it's getting to be pretty agile. And finally, let me zoom in a little bit on problem solving, whether it's answering unstructured questions or pattern recognizing and prediction and classification. This is probably the most important one for those of you in the room, and I refer you to this chart. If you want to look at it more carefully, there's a source, the Harvard Business Review article there at the bottom called The Business of Artificial Intelligence that I wrote with Andrew McAfee, where we go into more detail. But almost all of the big successes these days have been driven by what's called supervised learning systems. These are systems where you have a set of data that we call inputs, X, that you map to a set of data that we call outputs, Y, and the mapping between the two of them is learned by the system by having many, many examples. If you have a lot of data on your X's and Y's, it's very likely that you can build a machine learning system to predict or classify the X's into the Y's. And there's many applications. I'm sure there are applications in your company, and if you think a little bit, just spend an hour or two thinking about this, I suspect you'll come up with dozens of examples of mapping from X to Y. And we have some research that we've done that helps with this mapping using some techniques. But here are some of the examples of mapping in that way. And it's already affecting many companies in the financial services industry, in some cases using it to replace existing workers, in some cases using it to augment them. So this is how we go about making these predictions. And this tool, a basic version of the tool, is available in our article in the journal Science. But what we did was we created what we call a rubric of 21 questions. And if you answer these 21 questions, it will give you a score as to whether or not that task is suitable for machine learning. One of the things we did was we took those 21 questions and we applied it to all of the tasks in the US economy. Believe it or not, there is a data set of all the tasks in the US economy. It's called ONET. The Department of Labor has classified the economy into 950 occupations, and for each occupation there are about 20 to 30 specific tasks. This is what a bus driver does, this is what a radiologist does, this is what an economist does, this is what an airline pilot does. And for every one of those tasks, we had a team answer the 21 questions so that we now have a score for every task in the US economy, all 18,000 of them. And these scores, we call them suitability for machine learning, whether that task is suitable for machine learning. So let me share a little bit what we found. One way to classify it is to aggregate up the tasks by occupation, and each of these red dots is one of those 950 occupations. And I've put on the horizontal axis, the x-axis, the wage percentile. The people on the far right, the 100, those are the people with the highest wages in the economy. People on the far left are the people with the lowest wages. And I guess a couple of things are apparent there if you compare them to the SML score. First off, it is a scatterplot. There are people with high SML scores with low wages, people with high SML scores that have high wages. So just because you have high or low wages doesn't protect you from having your tasks suitable for machine learning. That said, there is somewhat of a downward sloping pattern. So the people with lower wages are on average more vulnerable to having their jobs automated by machine learning. Let me give you a couple of concrete examples so you get a feel for it. Cashiers are one of the professions in the United States that has the lowest wages. It's also a task that is highly automatable. At the other end of the spectrum, airline pilots also are quite automatable according to this analysis. But they have quite high wages. They have some of the highest wages in the United States. And I couldn't help resist to check my own occupation, economists. So we are reasonably high paid, not as high paid as I think we should be now. But fortunately, I didn't have to juggle the numbers. We're not as, our tasks are not yet as automatable, at least not with current levels of technology. But you can go ahead and in the paper we describe more detail all the different tasks that are automatable and why that's the case. You can also look at this by geography. And what we see here is that different parts of the United States are more suitable for machine learning and others are less suitable. The blue areas are the less vulnerable. The red areas are more vulnerable. And you can do it by market value. So here it is. These are the firms that are more suitable for machine learning. So every company, every publicly traded company in America, we have a score for whether or not they're likely to be done by machine learning. And this gives you a sense of which companies are most vulnerable. There are some companies where many of their core processes could be done by machines today, and that's likely, I think, to hurt their profitability in the long run. It will lower the costs, but it will also allow for a lot more entry, often from firms from outside the industry, and take away a lot of their competitive advantages. So in a way, this is not just an SML score, it's also a vulnerability score. Interestingly, so far, it's not very correlated with market value, but my prediction is over the next 5 or 10 years, it'll become much more correlated with market value. Let me now talk a little bit about products and platforms. So if you look at the most valuable companies on planet Earth today, 7 out of 7 of them are platform companies. They're all tech companies, but they're also all platform companies. This wasn't the case 10 years ago or 20 years ago or 100 years ago. So this really is a platform revolution. Also, as we describe in the book, the platform revolution has affected many smaller companies as well, not just these big ones. But let's zoom in on the one that's at the top of the list right now, Apple. And it's interesting, as we describe in the book, they are a platform company, but in a way by mistake. Initially, Steve Jobs did not want to make them a platform company. He resisted allowing other companies to put software on the iPhone. He wanted to have a completely closed system. His senior management begged him to please open it up, and eventually he agreed, and they did open up the App Store. And in 2008, they allowed other companies to put apps there. And within the first day, they had the first weekend, they had over 10 million downloads of about 500 different apps. And today, they have billions of downloads of these apps. And really, the reason that these phones are so valuable, the reason that it's the most valuable product in history, is not simply because it's got kind of cool hardware. Lots of companies have that. It's because of the ecosystem that's been created. It's because of the apps that run on it and the value there. So that turning it into a platform was the key driver of making Apple so profitable. And it's not true that Apple got 100% of the profits. It actually got, shortly after that, 103% of the profits. So it was really quite a success. Today, other companies are chipping away at that, but by and large, if you can dominate the ecosystem and have a successful platform, you can get the lion's share of the profits. Now, what's going on? Well, it starts with simple network effects, and I think most of you understand network effects, so I'm not going to spend much time on it, but the basic intuition is that as you increase the size of the network, the value grows more than proportionately. If you double the size of the network, the value grows closer to 4 times. if you make the network 10 times bigger, the value grows more like 100 times. So that puts a lot of benefits on trying to make your network bigger. But this is not a simple one-sided network like, say, telephones or fax machines. What's really important is that it's a two-sided network. And this is a little subtler, and most people don't understand two-sided networks. I didn't understand them when they first started studying them. But a good way to understand two-sided networks is think of some of the common successful apps. Uber recently went public as one of the most valuable companies ever to go public. And I'm sorry that it's not available here in Copenhagen, but I think you guys know how Uber works. But what you may not know is that there's an app that you can look at on Uber, but there's actually two apps. There's this entirely different app that the drivers have. And the value of my app doesn't go up when other people use the same app. The value of my user app goes up when other drivers have the driver app. Likewise, the value of the driver app is not a network function of other drivers, it's a function of more users or riders. So the network effect isn't on the same side, it's across to the other side. And this is the essence of most platforms, that the network effect is from the benefit of a different person using a different app, but that app is somehow related to the first app. In fact, it doesn't just have to be two-sided, it could be multi-sided. There could be many, many apps that have this characteristic. And once you understand the economics of two-sided networks, and we describe it a lot more in detail, there's some weird and wonderful economics. It could be beneficial, for instance, to give away for free the app on one side and charge money for the app on the other side. And that could be very profitable. Every one of these platforms, if you zoom in on them, they have at least two apps, two different sides to them. The oldest one is probably the credit card network. And there's an example where initially credit cards charged both the card users and the merchants, and they made money on both sides. But now they've discovered that they're better off giving away the cards for free and charging even more to the merchants. In fact, many of them have discovered that free is not the lowest price you can charge. What's lower than free? Negative numbers. So they pay people, they pay me to use their credit card. I hope they're paying you, whether it's in frequent flyer miles or cash back. So paying somebody to use your product usually would not be very profitable, but if you are part of a two-sided network, it can in some cases work. And as we describe in the book, it depends on the demand elasticity and the cross-elasticity between those products. But once you understand these weird and wonderful economics of platforms, you can develop some very profitable business models, and some very counterintuitive ones, I should say. The third revolution I want to talk about is moving from the core to the crowd. And more innovation is now in the crowd. According to Bill Joy, he actually pointed out that however many smart people you have hired in your company, however many geniuses you've been able to bring on board, the fact remains there are more smart people outside your company than inside your company. So if you can find a way to tap into those brains outside your company, you potentially can do much better than if you only rely on the core people inside your organization. Let me give you a concrete example of that, which is from the National Institute of Health in the United States. They recognized that they needed to sequence the blood genome of white blood cells. They are able to reorganize themselves to identify invaders, and they were able to come up with some techniques at the National Institute of Health that would sequence it in about 10,000 seconds. I think that's a little over 4 hours, with about a 70% accuracy rate. That was really a big breakthrough, but they realized they wanted to do even better. So they turned to their partners at Harvard Medical School and asked if they could do better. And Harvard Medical School, I would still consider that part of the core, did a little better. Got it down to a little over 1,000 seconds and accuracy up over 75%. But then Kareem Lakhani, a professor at Harvard Business School, used to be a PhD student of ours at MIT, said, let's open this to the crowd. We're going to put it up on Topcoder and have a whole bunch of people try to solve this problem. So they gave them the basic parameters and said, see if you can sequence the genome faster. And here are some of the teams that entered. All those circles entered. As you can see, some of them were really bad. Some of them were both slower and less accurate. But look at the red circles up near the top there. Every single one of those was both more accurate and faster than the Harvard team or the team at the National Institute of Health. And they delivered these results within about 6 weeks for a grand prize of a couple $1,000s. The very best team, it's remarkable, in the top left corner there, did it in just over 10 seconds. That's right, 10 seconds with an accuracy of over 80%. So they completely blew away the experts at Harvard and NIH. How were they able to do it so fast? Well, part of it is that you had a lot more brains working on it when you went to the crowd, but that's not the real driver. The real driver is that the people working on it from the crowd came at it from a very different perspective. They had not been trained in genomics. They instead were trained in areas like seismology, topological mathematics, fractal geometry. And these alternative techniques turned out to be very suitable for this problem. They were able to see the problem in a way that seemed very easy to them, as long as they relabeled some variables. And so for them, this was a straightforward problem that the core people hadn't thought to solve. And in your organization, if you're butting against a problem that you haven't been able to solve for a long time, it's probably because your top experts are all using the same tired set of techniques. And if you had someone fresh coming from outside the organization with a whole different perspective, they might do a lot better. Now, this is not just one example, but when you think about it, the crowd is becoming more and more important, whether it's an encyclopedia. Google itself is crowd-driven. The reason Google search works so well is not simply they've got some great engineers in Mountain View, but it's because of the crowd. Every time somebody links from one page to another, Google uses that information, the link structure, to decide how to rank web pages. So the crowd, in essence, is voting on what the search results should be, and Google is leveraging that knowledge. And Kaggle has also been very successful in running competitions. In crowdsourcing, we are seeing this work increasingly in funds as well. There's a fund out of Massachusetts called QuantOpium with over 200,000 people contributing algorithms, and it's performing quite well. So that's the triple revolution that's going on. Let me leave you with a couple closing thoughts. As we heard, ESG is getting important. People are caring more about social responsibility. I want to say a word about that as well. That while these digital technologies are making the pie a lot bigger and increasing overall productivity, the hard economic fact is that there's no economic law that says that everyone's going to benefit. It's possible for some people to be made worse off even as the pie gets bigger. In fact, according to economics, it's possible for a majority of people to be worse off. It doesn't have to happen, but it can happen. Unfortunately, the data suggests that over the past 20 years or so, most people have not been sharing in this wealth. Here's data from the United States. The blue line is ever-growing productivity. So we're getting more and more effective. We're creating a bigger and bigger pie, creating more wealth than ever before. We have more millionaires and billionaires and more total output. But the red line shows that the median income, that's the 50th percentile, has been almost flat, maybe a small increase. And this is true in most of the OECD countries. It's true in Denmark and Sweden. It's true in France, Germany. It's true in China. So most countries have seen a growing gap, we call it the decoupling, between productivity growth and median income. But let me just say that doesn't have to be that way. It can happen. We are working at MIT to have a new grand challenge, and with this new grand challenge, we are using these technologies not just to create prosperity, but to create shared prosperity. And that requires us to reinvent our skills, reinvent our organizations, and use the technology to benefit the many, not just the few. So I hope these examples I've given you of the triple revolution, of moving from mind to machine, from product to platform, from core to crowd, will inspire you not only to use technologies to create value for your own organizations, but also do it in a way that creates broadly shared prosperity. Thank you very much.